All right, friends, we are starting. How is everyone doing this week? Feeling good? How do we feel about after being done with reverse engineering? We're good on reverse engineering? Kind of. The reason why I ask is because what we're about to get into is binary exploitation, right? And this is like basically reversing, but like cool. No, reversing is cool, but a lot of binary exploitation is still learning how to do reversing, but you're looking for specific exploits inside of a binary file and then exploiting and like hitting that exploit with specific input characteristics to then get what you want. It's very similar to reverse engineering, except for that in binary exploitation, there's always a series of steps that you could follow and like specific exploits that you'll hit. Why is Ron doing push?
He owes me 32 factorial.
I didn't do
Combination.
Okay, I hate you.
6 times 10 to the 20, whatever.
I don't even want to know. So the reversing and binary exploitation folder is not completely done on the Google Drive yet, but I promise we're working there in terms of the documentation. Until then, and even then after that, there is only one great link to learn binary exploitation, in my opinion, and it is this Git book, written by this dude named Ironstone with a 0 in his name because he's elite. And this is single-handedly one of the greatest resources I've ever come across in my time of life, which is kind of sad. Anyways, so in introduction to binary exploitation, there's different types of binary exploitation that we'll look at. The first kind is stack, right? So this is introduction. This is like, as a beginner, we'll start with stack exploits, and we'll look at the different kinds of stack exploits, and we'll understand how to do those stack exploits, and then eventually you should become pretty proficient in identifying and executing those stack exploits. When you get to the intermediate level, that's when you start looking at heap exploits, which is dealing with malloc memory and things like that. So you know how in our C lectures, we talked about the heap versus the stack and how the heap you have to use like malloc and calloc and things like that. You can actually exploit that space using heap exploits, but it's a lot harder than stack exploits are because it's not as static and it's just generally harder. So that's an intermediate level thing, something that we'll probably get into next year. And then an advanced level is kernel exploits, which is writing like rootkits, keyloggers, and things like that, and exploiting the kernel, which is a lot of fun. I've done one rootkit. Devin just wrote another rootkit, so it's pretty cool. All right. So let's just review some stuff. So who can tell me what the stack is? Not Ron. Anybody?
Right, where actually it's broken down into 5, right? There's like 5 layers of stack, and is that what you're referring to?
There's 5 levels of like memory layout in a program. One of those is the stack. What's up?
Is there pointers to variables?
So it is pointers to variables do go there. It's where any data allocated to stack space lives for a program, right? So we talked about like this is a stack for a program, okay? And inside of these boxes go like the variables and their data that the variables store, and each of these correlate to an address, and those addresses this address points to like this section of the stack, and inside this section of the stack is the data for that address, and this address is basically a variable, right? So it's like A, and A is equal to 4, and it has some address that's like OX7F, and so on. Okay, remember that? Is that coming back to us? Okay. We talked about registers in reversing, right? You guys remember the registers? Yes. Okay. Who remembers what RBP is in terms of register? The base pointer, right? So RBP is the base pointer. The only difference between RBP and EBP is that RBP is 64-bit and EBP is 32-bit. A lot of the binaries that you guys will be initially working with are 32-bit binaries, and so, but I'll still refer to it as RBP because that's just like a working way to say it is RBP. The only difference in terms of binary exploitation is that when you write things in 64-bit, you need to make sure that they're padded out to the 64-bit space, and then when you write things in 32-bit, they can stay in the 32-bit space. Okay? So, the way the stack actually looks in this is that for some program, we have the return address here called ret, right? And this is the stack for a given function or a given program. Okay, so this is a main. Say this is the main of some program that we have. Okay, this main has a return address. This return address is the address that when this function finishes and returns, it's where it's supposed to go back to. Okay, so if you look at the bottom of a if you look at the bottom of like assembly code, you'll see like a pop ret, right? So that pop ret pushes ret back. It takes ret, it pops it off the stack and puts it in memory, and then it'll do a return. It'll do an LEA basically to that address, and it'll jump back to that address that was stored here. Okay. Next in ret is SBP. So I'm going to say S/R BP. Okay. The reason why I say S is we refer to it as the saved base pointer. Okay. It's basically the same thing, right? And then after that are all the variables that are defined within our main, or the function that this stack represents, right? So like A, B, C, and so on. Okay. Above ret are arguments that are passed to that function. So for example, like a main argument, what's the normal arguments that we pass to main? All right, one person said it.
Oh, yeah, the RC.
Argv and what else?
RC.
Argc. So I think it's argc comes first, right? So it'd be like this, argc, then argv. Okay, so it starts from the first one and then goes up. And so this is the stack for a program, okay? Now, the purpose of binary exploitation is, for stack binary exploitation, is to somehow exploit flaws or weakness in code to modify the stack in some way, okay? So imagine that there is a print flag function in our code somewhere, okay? But that print flag function is never called, all right? We can find the address of the print flag function in our assembly code when it's statically compiled without any kind of stack protections, right? So like it'd be kind of like unreasonable if there were no protections against these things in real life, right? So what we'll say is without any stack protections, everything, all the addresses and stuff are static. So we can find the static address of our print flag function, and we can insert that into our return address. Okay? And that way, when this function is done, it'll return to the print flag function, and then it'll print our flag, right? So that's a CTF example of how we do it. Another example is this is like a real world example, but tell me if you get confused by following it. So another example would be in the real world, if we want to exploit a running program, we somehow want to get a shell, right? We want to get a command prompt. We want to get something where we can input malicious code, or we can input malicious commands so that we can get control of that system, right? That follows? So when we load a program, any kind of program, say it's like a Linux program, it has loaded in it libc already, right? So libc is the library that contains all the basic commands in Linux for a C file, right? Tracking on that? we can get the call for system from libc, call system by replacing the return address here with the address of system in libc, pass it the arguments of bin/sh, and then what the system command does is it runs in the system, or as a root user, any command that you pass to it. So if we run /bin/sh, it'll return back to us a command prompt, and we've now exported this program to the point where we have a command. So,
Is that a system call?
system? Yes, system is a system call. So we'll call them syscalls. Normally when we're doing exploits, you're most likely going to be exploiting syscalls. So exec.ve, system, there's a couple others that if you're trying to make networks and stuff like that, yeah, you'll do. Does that follow for everybody? Make sense why we do it in the real world versus as opposed to just trying to get a print flag in a CCF? Cool. All right, cool. So let's look at an example of how to actually overflow a buffer and what that kind of means. So the point is one of these things, we're going to try to overflow one of these things up to this point so that we can write something here. Okay, and we'll see how we can do that. Okay. So when it comes to analyzing all this stuff, we're going to be analyzing it the exact same way that we do reversing. So you want to analyze it with Ghidra, you want to analyze it with GDB, and you want to do obj jumps. Okay, we're all familiar with all three of those tools, right? So those are the tools you use to still analyze what's going on in the binary and to look at it. All right, so let's look at this. Also, sometimes they'll give you source code, which is nice. So we'll look at an example right now of just like source code, and we'll talk about why the source code is vulnerable and then how we can exploit that. So I wrote something up called intro.c, and it's basically just this. All right. So it is a simple function. I should increase the. Okay. Like it for everybody. Basically, we have a buffer that says you can't pwn me, and this is just like a regular string. And then we have another string called buff2 that accepts 8 bytes, right? So technically, we're only supposed to write 8 bytes to that string, right? And then we do a printf to see like, hey, please input your first name, because we're assuming nobody's first name is past 8 characters. And then we say f gets buff2 32 standard in, and then we print f our buff2. Okay. What does f gets do? Who can tell me? Anybody remember? Or anybody quick on the man page?
It reads into a pointer until it reaches the null byte.
Yeah. It also. So what's the second argument to f gets?
Size.
Yeah, size. Somebody raise their hand. Okay. No. So, right, like Ron says, it reads in for size. This is like all the different types of reads that you can have. It's kind of ridiculous. But we'll look at fgets, right? So fgets does, it takes a pointer. Oh, man. It takes a pointer, okay, as we can see right here. And then it takes a size, and it'll read in until that size from the file stream that you indicated, okay? So to break down this code, basically, we're reading in to our buff2. We're going to read in 32 bytes, and we're going to read it from standard in. We can see a problem with that. Exactly, right? So we're trying to read in more characters than buff2 has in its space. So let's model that on our stack over here. We'll say the stack is 4 bytes wide. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Just technically it's 17 with null byte, so we'll just say 16 for these 7 boxes. Okay. And then 4, 8, 12, 16, 4, 8. So this right here is buff. Okay, this is the stack space that buff occupies. If we're saying that our stack is 4 bytes wide, right? Because we said that it's about 16 bytes long. So 4 bytes of that 16 bytes will go in here, and that's the space that buff occupies.
Why is it only 4 bytes, not 16?
Huh?
You said it's only 4 bytes.
Because the stack frame is 4 bytes wide,
yeah.
so each stack spot or each space on the stack can only store 4 bytes total. Does that make sense? The way that C knows that that's like the end of the string is the null byte is here, and so it'll keep reading all the way up to that stack space until the null byte normally when we're doing printers stuff like that. Else it could keep reading forever. Like if I were to like do if I were to print, I think -1 here or 9, one of the two. I think it's -1. If I were to print buff 2 -9, I should be able to print the null byte of buff. If I print -2, I should print the E of buff. Because the way indexing works in C is that it actually just indexes based off of it. It's like saying that, hey, this is like, say I want index 0, it's actually just that address plus 0. If I want index 1, it's that address plus 1. If I want index 2, it's that address plus 2 times the size of the data point. Does that make sense? I feel like I confused you more. Kind of.
So you're saying if you printed the -1 at index of buff 2, you'd be getting the null terminator of buff.
Yeah, I should be getting a null terminator of buff because here is buff 2 on the stack. Okay. And that's how the indexing actually works. Is it's the address of our variable plus whatever we put into the square brackets. Cool on that? Okay. So, like CJ said, we're reading in more characters than the size of the buffer. So if I read in 8 characters, say I just do A's, I've read in 8 A's, and it's all good. Say I put in 4 more A's. What do you think happens? Huh?
Keeps on writing into the first buffer.
Yeah, so it'll keep writing into here. And it will overwrite whatever stored in buff. The quite frankly does not care. Right? That's the thing about the stack, is it will just keep it like fgets is an unprotected call. It will read until the amount of bytes are read, or until a control C is set, or a control D. So until you send a sig int or a sig kill, like a signal interrupt or a signal kill, it'll keep reading until it gets 32 bytes, and it will overwrite that space on the stack no matter what, because it's assuming that you're using it right. Okay, so fgets is one of our first vulnerable function calls that we'll be looking for when we're looking for a buffer overflow. Right, so like if they're doing a fgets to a buffer that's smaller than the size that they're fgetting, that's most likely the buffer that you're trying to overflow. Okay, that makes sense? So then we can keep writing A's forever and ever and ever until eventually 32. So 4, 8, 12, 16, 20, 24, 28. And we've overwritten RVP at that point, and 32 exactly gets us to red. And now we've overflown our return address with all A's. Make sense? Cool. All right, let's kind of do it. So I've already compiled the program. And if you're given source code for these problems and stuff, and you want the source code to load into GDB as well, you can always just recompile the program, but make sure you do it with like the correct permissions and stuff. But if you want it to load into GDB, you have to do tech G, and that means you load debugging symbols into your program, and it'll load the entirety of the source code into your executable. Okay, so if we GDB a.out, we can do a list here. We can see the code from before. We'll set a breakpoint at line 9. Okay, so this is right after we've read into this buffer. So what I'm going to do is I'm going to send in a certain amount of A's. I'm going to see if that overwrote our buff. All right. Okay. So we'll run. It asks me for my first name. Let's see. I don't have it still saved. I will. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. Actually, we need to do 7 because 8 is the null byte. And if we continue, we see it has no problem, and it says ha, and then A's, right? So it's cool. If we redo this, and we do 1, 2, 3, 4, 5, 6, 7, 8, and say we want to try to find out about buff. You see how it like has a problem accessing that? It's kind of weird. But like nothing immediately crazy. Okay. If we continue, it's still fine, right? Because all we've done is overwrite a little bit of the buff. So instead, if we run and we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. 34. And we continue. We try to continue again. I get a sig-seg. So it's seg faulted. Right? So sig-seg V is a seg fault, right? So it's seg fault because I overwrote RVP. If we look up here, RVP and therefore the return address, well, not therefore the return address. I wrote enough to get above RVP and then over at the return address as well. But you can see RVP is overwritten with all A's, right? OX41s. If I wanted to examine that there, the better way to print things out is like this. Python 3 tech C, and then print A times 34, and then I can just copy this, and then it's very happy with me. Okay. So let's see here. Oh gosh, sorry, 1 second. Did I not put enough? I think I put just enough. 1 second. I don't think I put enough A's. 240. Call it good. Okay. So you can see that the address of RVP itself. So like this thing over here that points. This thing over here that points to RVP points to just all A's, right? It should be that space. Okay, so that points to all A's, and we're at this point here. So if we do an examine of 4 above RVP, we should see all A's as well. Okay, so 4, well, yeah. So above RVP should be what? The return address, right? So we've overwritten our return address with all A's instead. Okay. So we overflowed the buffer and we broke the program. Now to make it really useful, you want to overflow it with like helpful information. For overflowing to returns, then we want to overflow with with the address of like somewhere else that we want to go. It's normally going to be a function. So you'll overflow it with a function. We can also sometimes you just want to change a buffer because like it has to be a certain thing to pass a check. So you could just overflow what the say it's like a true or false, like a Boolean. You could just overflow the Boolean with all ones and then make it true. Things like that. Okay. Anybody have any questions on how the basics of a buffer overflow work? Yes.
How do you find where a function is going to be like where the function is defined if it's in like the C library? Does that make sense? I don't know if I'm having some.
So in libc, how do you find?
How would you know where to return what's an overflow to get to that point?
Yeah, how do you know where what address it is? Yeah. So you can opt jump the entirety of libc and search for it. There's tools that you can use to look for the address of something in libc. However, that's anticipating that the stack protections that we'll learn about in later lessons are actually off. And if they are off, then that address stays static, and it should always be the same from when you looked it up statically to when the program's being run. Now, most modern programs, when they're run, have something called ASLR and pi, which means that their address space is randomized every single time it runs. So even though when the binary is statically compiled and we're looking at it and it's at a specific address, when that program's ran again, that address is changed because the starting address of the program itself starts somewhere else, and that's part of the ASLR. But we'll talk about how to break that later on in lessons. So easy ways to do it is to opt jump, tech b, tech intel, a.out, pipe that to less, and then we can look up main, and then next that. And then this is technically a starting address for main, right? And we could do that for any kind of function that we're looking for. Anybody else have any questions? Any other questions? Yes.
Do you have the source code or another program you can use?
Yes. So for this one, I suggest I put it into the shared drive under reverse engineering and Binex, I thought. And Grace changed the name to reverse engineering. I'm assuming. Yeah, there was nothing in there. It's in the reverse engineering. It should be in a Binex one, but I haven't changed it yet. And it's called the introduction.zip. Or you can go to Ironstone. Just look up Ironstone with the 0, and it's the first Git book. And you can follow along with what I'm teaching up here.
Go to the binary exploitation online resources.
I know, but oh, is it in there?
It's not.
If you go to, all right, I'll just show it. Huh?
The Ironstone.
The Ironstone one's there? Okay, so if you go to the shared drive and you go to binary exploitation and you go to online resources, it should be on here as the first link of Ironstone. And then you can click that and it'll take you to Ironstone, and then you'll be happy and you won't hate Christian. Yeah. Yeah. Put on your mask. Thank you. Okay. Any other questions? So the next thing we're gonna do is this ret to win, and we're gonna talk about how to do it, and we're gonna walk through it. But I highly suggest downloading the stuff for it so that we can talk about how to do it. All right. So, any other questions before I continue?
The one we're about to do, where is that?
It's on Ironstone. I haven't uploaded it anywhere, so that's my bad. Okay. So functions like fgets are exploitable. We'll also look at things that like stir copy. There's a difference between stern copy and stir copy. So stir copy doesn't have a length size imposed on it, so it will copy everything from the first buffer that you give it to the second buffer. So if the first buffer is like 1024 big and the second buffer is 8, it will write 1024 bytes to the 8 size buffer, and it'll overflow everything above the 8 buffer. Make sense? Okay, so we're looking at things that are vulnerable like that. All right. So ret to win is the first kind of binary exploit or stack-based exploit that we'll talk about. Okay. And so what it means is basically we want to overwrite ret with a win function. So this is really a CTF kind of thing, but it's really good practice for doing like more complicated things. So they're quite literally normally titled win function in CTFs, or they could be like print flag or anything like that. But we call the challenges ret to wins. All right. So like I said, this stuff is without any stack protections, so you need to specifically download the zip file that he has. Okay, so we'll download it. Everybody, just to make sure, we're on the ret to win page, and it's the ret2win.zip here that you can download. Okay. And we'll unzip that. Yes. Yes. Okay, and make sure that if you don't want to replace the introduction ones, that you name it something different. I don't care about replacing the introduction ones. So we'll look at this first before we go into his explanation. All right. So this program itself is very similar to what I wrote. Okay. So we see a function called unsafe, right? Which basically tells us that it's probably unsafe and what we want to exploit. And let's just somebody look at this and tell me how this is exploitable. Yeah. Huh? It's not the puts. It's something else in there. So keep in mind that most of stack exploits we're looking for uncontrolled reads is what they're called. Okay, so where do we do an uncontrolled read? Ron.
The gets.
The gets is an uncontrolled read. Gets will just read until you give it a null byte or white space of any kind. So you could literally keep writing things, and it'll overflow this buffer of char buffer. Okay, that makes sense. All right. So yeah, if this buffer is overflowable, we can overflow all the way up to 40. And then that puts us where? Where if we overflow all the way up to 40, where does that put us on our stack? Perfect. Right below the RBP. So let's say this is our buffer variable, right? We've overflowed it with all A's. That puts us like 40 A's. That puts us right at RBP. This is not actually 40 A's. My apologies. That puts us right at RBP, right? So now, since gets is an uncontrolled read, and we can write however many things we want, we can overflow it with more A's here, and then we can put in the return address of what? Somebody that's not that.
The flag function.
Of the flag function, perfect. And then that way, when this unsafe function returns, it's going to actually return to the flag function, and then it'll output exploited, which is the flag, quote unquote. Okay, that makes sense. So just to show how to use this guide, because I think it's a really good guide, we'll follow along with how he does it. Okay. The first thing he talks about is finding the padding of the buffer. Okay, and this can be done by trial and error, as he says. In his guide, he uses a tool called R2. You can just replicate everything that he's doing in R2 with GDB. Okay, so we'll look at this and we'll say GDB vuln. Sorry, GDB vuln. That's embarrassing. Okay. Actually, what we want is, what was it called? Anybody remember what the function was called? Huh? No, the other one, the
Unsafe.
unsafe. Sorry, let me hide this. So we'll disass unsafe. Okay. So what we want is, we'll probably put a breakpoint around after the gets. Okay. Who remembers how to do breakpoints in B star?
I mean, where do you want it broken at? Main, so B star main.
Nah, so we'll do it after the gets call. To see how the buffer looks. So this is normally where you want it. So in reversing, you normally want to do it at places where there's like comparisons and things like that, right? So you can see exactly what's getting compared and how your input's compared to like what it's checking for. In reversing, we'll normally want to put breakpoints after we provided some input, so we can see some input, so we can see how our input influenced the stack. Okay, so we'll break right after this call to gets. Okay. And then we can run, and it'll be like overflow me, and we can see how long it takes to overflow. But like, it's also, we can also just do math as well. Okay. So if the buffer is 40, how many bytes do we need to overflow the buffer?
Like 39.
40. Because the buffer is 40.
Okay.
So we need 40 bytes to get past the buffer. Okay. So 40 bytes for the buffer. Then what else is stored on the stack for this buffer? It's something that's associated with the buffer. The actual variable's address is also stored. So like the variable, because it's a pointer, there's a pointer that's stored on the stack as well. So that's another 4 bytes that we want to overflow. Okay. Plus 4 bytes per pointer. Huh?
Where's the pointer to that one?
The pointer to that pointer is like over here off the stack, and it's technically not stored anywhere. Well, I mean, it is stored somewhere. There's like a greater stack above all stacks, and then there's like memory allocation out of everywhere, like page offsets and stuff.
Okay.
And that's kind of like the page offset stuff. The computer keeps track of all that stuff. So if you were to do like an ampersand of a pointer, it will give you another address. It's normally an address that's like OX7FFF, which is in the stack frame for like the libc start, which runs on.
Yeah. So as soon as it was.
Yeah, there is just like kind of unnecessarily abstract. Okay, so we're at 44 bytes. So we're trying to get to ret. What's another? So then we have another 4 bytes for what? Base pointer. since it's a 32-bit system, we'll say EBP. How did I do that? What is going on? Okay. And then another 4 bytes for what? Finally. For the return. Perfect. Okay. So I might die. Anyways. All right, perfect. So we have all that for the function. So that's how many bytes it will take to overwrite the return address. Okay. And let's see if that's correct to what he says. He talks about we get a segfault at 52 bytes as well. So yeah, good. So in Radari 2, you can find the address for the flag function like that. In GDB, we can do it by just disassessing flag, and then we can find the flag function like that. And you see we have matching addresses. Okay. So let's keep a running tab over here. So let me. So we'll say our address is equal to this, okay? And this is normally good to like keep a note kind of like this. Overflow bytes is equal to 52, okay? So using that information, we can write our address and add it onto our bytes, and then we can send it to the program, and then hopefully get what we want out of it, which is printing the exploit with all the exclamation marks. Okay. So let's test you all. So, all right, let's yeah, okay. So we'll write the address like he does as such, okay. 08/x04/x91/x9c3, okay. So we have our address written in hex string, okay. And then we're gonna learn something new here. And this something new is pwn tools, okay? So when we're sending this stuff to, when we're sending this to the actual file, to the vulnerable executable, you can do the Python 3 taxc thing like I was doing, but the problem is the print function itself doesn't write raw bytes. It used to in Python 2, but Python 2 is deprecated, so you shouldn't use Python 2. If you're trying to do it in Python 3 through the command line, there's a standard there's like a sys.standardout.buffer write thing that you can do, or we can use pwn tools, okay? Pwn tools should come on all Kali. If not, all you have to do is pip3 install pwn or pwn tools, one of the two. And then to call pwn tools, we always have to reference it like this from pwn import star. So that's super important, okay? It always has to be called like that. I have no idea why, but that's what pwn tool says, or else it'll break and it makes you sad. Just for demonstration purposes of installing, it's pip3 install pwn like that. Cool? Cool. It should be on Kali already, but sometimes it's not, and that's not cool either. All right. So for pwn tools, these are how we'll normally be writing our exploit scripts to overflow buffers and to finally get an exploit or a command shell or what we want. So what we first do is we declare a variable p and we do this function called process, all right? So there's two functions you can use. There's remote and there's process. Remote is if we're connecting to a remote port that's running a program, and it'll give you the same interaction that you have for process. For process, we put in the name of the executable that we're running. All right, everybody following on that? Cool. So we'll do vuln dot slash, or we'll do dot slash vuln like this. Okay. And then we'll keep working on this. So then we have our payload, right? And we were talking about how we want it to be 52, so we'll have a buffer of 52. Okay. And then what we'll add to the payload is plus or equal our address. Okay. Everybody cool so far. I don't like p.clean, so I'm gonna do print p.receive instead. Do I have to put bytes in that? Do you remember, integers? For p.receive? Do I have to put bytes in that? I shouldn't, right? And we'll just test this out really quick. I don't know how to write Python. Okay, perfect. Yeah. Good. 1 minute. I just gotta update my phone tools really quick. Just updating. So for the next parts of this, we have this neat function called p.sendLine, and you can send a payload. You put your payload or whatever you want to send in the send line, and then it'll automatically tack on the new line for you, and it'll send that as a line. Okay, and then it should, once you do another p.receive and print that, it should print exploited. Okay. But we gotta wait for my phone tools to be done. Okay, it's done. Yay. All right. Now I don't want to. I guess I'll go through it. It makes sense. So after we print, we want to do a p.sendLine of our payload. Okay. And then we want to print p.receive. And that should, right, give us the exploit from the exploit function, right, from our flag function. So let's run it and see if that's what it does. And it didn't. It gave us a seg fault. Can anybody tell me why it gave us a seg fault? And I will say, hint, it's something about our script. What do you mean by going down in addresses?
Like, because we're adding the address.
Oh, no. That's just like concatenated strings. Oliver?
I don't know. What's the purple one? Can you increase the tone?
What's the purple? Sorry. It's just a string.
Okay.
You can bring down the curtain. Anybody have a guess? Ron?
Once it does the one flag, it doesn't know what to return to, so it makes a sig fault.
Nah, that's not it.
No.
Because we're not overriding that. All right. Are things written on the stack backwards or forwards? And what's that called?
Oh, endiness.
Indianness, right? So things on the stack have to be written in reverse, which is little Indian. Okay, so big Indian is when we write it normally with the most significant bit first. Little Indian is when we write it least significant bit first. i.e. big versus little, right? So B for most significant bit first, the biggest bit, and little for lowest bit written first. Okay. So our address that we're writing into a stack frame, right, is written in Big Indian, right? So we can reverse this by reversing it ourselves, like by writing it in reverse. But most of the time I'm lazy, and so what we'll do instead is use a neat little tool from Pwn Tools called P32. Okay. And so what this will do is it's called Pack32. There's also a P64, which is Pack64, and it will convert the number basically that we give it, because this will always convert into a number. It'll convert this number that we give it into a 32 packed 32 packed little Indian string instead. Okay, so it'll flip it and write it in little Indian. The key part of that is that we have to make this now the actual hex number by doing this. Okay, and then additionally, what this does is it turns this into a byte string. So we also have to turn A into a byte. Okay, or else, as Ironstone talked about, you'll get a type error. Okay, and so now, if I could use Vim correctly, this should work. Okay, so with it packed on correctly in Little Indian, written onto the stack right, overflowed the optimal amount to 52, which gets us right before return, overwriting the return address with the return address that we found for flag. We now get it to print out exploited, which is what the flag function does itself. Okay? Does that make sense to everybody? We're all cool on that. Yeah? Any questions before the day ends? No? Okay. Well, so that's all for me today. Tomorrow we'll most likely cover a little bit more and do practice problems. Cade has you for the rest of the week, and I'll be around to help assist him. So yeah, other than that, have a lovely day. 1 second.